Where are we now? The reason that I'm spending some time here giving you this very physical picture of a physical device is because I want to link what usually is very abstract of Hilbert spaces and bosonic and fermionic creation and annihilation operators to a very physical, real thing, which is what I work with in the lab every day, and what you can now work with, of course, through the cloud. And the physics of it will allow you to do some things that otherwise you might not think about if you are too only focused on the world of operators, as we'll get to. And so it's this very interesting, simple structure of two metal pads and an inductor here that can be described by several manifestations of electricity, magnetic flux, charge, voltage, and current. And by several, I really only mean 4, and 2 more in numbers, such as the inductance and capacitance. That will be the basis of our qubits, readout resonators, amplifiers, and really everything else. So I really want to explain them in great detail. The way we symbolize an inductor is with one of these squiggly lines here. So you'll see a lot of pictures of inductors. One key concept about quantum is energy. Energy is quantized. So what is the energy here? At least at the classical level of this electromagnetic circuit. Well, we said that basically consists of inductive and capacitive parts, right? Things that are associated with the magnetic fields here and things associated with the electric fields here and the charges. It really follows from F equals ma that, and the way that charge and force and electric field are related, that the rate of change of energy is of course the power, and the power is the voltage times the current, right? And this is now the energy that is stored in the components such as the capacitor or the inductor. It could of course be the energy delivered by the component, but we'll take the convention that it's the energy stored in the component or delivered to the component. And likewise, this is the power, the instantaneous power flowing into the component. So that's power going in. As earlier, of course, if you integrate this equation here, you will get that the energy is equal to the time integral from the reference state to time t of the power of the tau. Technically, there should be, of course, an energy at time 0 here, or at time minus infinity, excuse me, but we'll assume that that's 0. I'll leave it as an exercise to you because it's pretty easy to change the variables of integration here from the integral of v of t, I of t, dt from minus infinity to time t, and these should be primes, excuse me, using the fact that, say, phi dot is equal to d, and this is, don't have the eraser here in PowerPoint, but phi dot, the rate of change of the magnetic flux, is equal to the voltage. To calculate that the energy in the capacitor is 1/2 c phi dot squared, or basically it's 1/2 cv squared, the voltage. And the energy in the inductor is phi squared over 2L, or it's the magnetic flux squared divided by twice the inductance. So the larger the inductance for a given energy, right, so if well, we'll get to that. The important point here is that you can actually very equally represent all of the energies, not just in the magnetic flux, but also in charge. You can swap the basis. There's almost a dual basis here. But I won't really talk about charge very much. I'm going to almost exclusively focus on describing everything in terms of magnetic flux. And that's motivated by the fact that the nonlinear inductor that we're really going to be interested in is the Josephson tunnel junction, and it is described by magnetic flux. It's not very convenient to talk about it in terms of charge. Now let me summarize before moving on what we just learned, because I've just covered a lot of fundamental ground, things that are simple, you may have seen a few times before, but at the same time they're really the 4 basic fundamental manifestations of electricity that are universal. They hold for all elements, whether linear, nonlinear, hysteretic, or anything else. Right? The electric charge is related always at a particular point or branch, whether it's plus or minus, right, is related to the current by the rate of change here, and equally the current is related to the charge by this integral. Similarly, in a very dual manner, the magnetic flux, which maybe we can symbolize with these magnetic flux arrows here going through a loop of current, is linked to the voltage by the rate of change, or the voltage is linked to the magnetic flux through the time integral. And this I mostly give you for reference. We also learned that we can link all four variables and form a loop. This will be the loop of oscillations by introducing elements such as the inductor over here or the capacitor over here, which can link across the two branches. So the capacitive element links charge to voltage, and the inductive element links current to magnetic flux. In other words, if I run a current through the inductor, it creates a magnetic flux. Now, it's a little bit more subtle because in a Josephson tunnel junction, you don't actually create magnetic flux. The flux here describes kinetic energy, which is associated with the electrons. That has to do with superconductivity. But to the earlier question that someone asked, we can all ignore that level of detail, and it really, at this level, doesn't change anything. And I'll emphasize again that all of these variables are real numbers between minus infinity and plus infinity, and I'll assume that both capacitors and inductors are only strictly positive. And this slide gives us really the foundation of both quantum and classical electrical theory, because it describes how all of the variables that describe the inductor and capacitor here, such as the magnetic flux that might be associated with this inductor, or maybe the charge that we might think of on this inductor, or the magnetic flux of this capacitor, or the charge on this capacitor, are related to each other, as well as to the voltages and currents and so forth. The one piece that we are missing, the link that's missing currently, is how do different elements relate to each other? And of course, as you have, I'm sure, seen before, this is given by Kirchhoffs' network laws, which are effectively a reduced version of Maxwell's equations and the conservation of current. Since charge can't be created or destroyed, it means that a charge that is flowing, say, from the inductor to the capacitor has to be accounted for correctly, right? A charge leaving the capacitor should change the charge associated with the capacitor. Let's call it Q sub C. That Q sub C should decrease. And now when the charge has transferred over to the inductor, the charge associated with that inductor, call it QL, should increase. And I'm running out of space here, so I apologize for the little text. And so Kirchhoffs' current law tells us that the sum of the currents into a node, such as this node N1 depicted up here, has to be 0. Remember that Q dot is nothing but the current. There we go. The plus minus sign is determined by the relative orientation of these little arrows. We don't need to concern ourselves with too much detail on that level of the signs, because I can give you an example here of, let's look at node 1 in the circuit, which is this node. There is a current going into this node due to the capacitor and a current going in due to the inductor. Well, their sum has to be 0. In other words, the current flowing from the capacitor has to equal the current going into the inductor. The plus sign here has to do with the reference direction, since we've decided to denote current going in the same direction. So the capacitive current is pointing up, and you see that when it goes into the inductor, it has to flip sign. And so that's why there's this plus sign here. Now, the second law that comes from Maxwell's equations, from Faraday's law of induction specifically, is Kirchhoffs' voltage law. And it just tells us that the sum of the voltages across a loop or along a loop, remember that this is nothing but just the voltage at branch B, has to be equal to 0. And again, there's an orientation which is indicated by this plus minus sign. And so if I look at loop 1 and I trace how the green arrow here aligns with the brown arrow, I can write down that for loop 1, I have a plus sign for the capacitive flux, and now because the brown arrow is anti-aligned with the purple arrow, I have a negative sign for the flux of the inductor. And this is kind of the formal construction which you can exploit to generalize to arbitrary circuits. But it says an incredibly simple thing at this stage, which is that the voltage across the capacitor is equal to the voltage across the inductor, right? Moving this phi over to the right-hand side. Very surprising. Of course, this is expected from electrostatics because the voltage is independent of the path taken from one point to the other. Now we can use that relationship, we can use the fact that the capacitive flux is equal to the magnetic flux, and we can use the constitutive relationship that, if you remember, Q is equal to CV. In other words, that Q dot at the capacitor, which is the current at the capacitor, is equal to C phi double dot at the capacitor. But we also know that the magnetic flux of the capacitor is just equal to the magnetic flux of the inductor. And by the way, since they're equal, we might as well drop the indices and just call them magnetic flux phi. Okay, and so this is the term that leads here, upon substitution of the charge equation on the left. And on the right hand side, we can again use the fact that we know that the magnetic flux is linked to current of an inductor by the constitutive relationship phi is Li. And we also know that I is equal to the rate of change of the charge across the inductor. And so using this second relationship, we can then obtain the condition here. All right, and now what you might already begin to recognize is a very simple equation of simple harmonic motion. And here we come to our first oscillator, because we see that a change in the second time derivative of phi is related to the position of phi. So what does that look like? Okay, here's the same equation again, bringing it back. We can rewrite this in the suggestive, usual simple harmonic oscillator motion way, where we have something that looks like F equals ma, essentially, with the harmonic frequency omega naught, which is equal to 1 over the square root of the inductance times the capacitance. And that will give us the resonance frequency, since this flux phi can now oscillate at something like phi naught e to the negative, say, I omega t. To make an analogy between the electromagnetic circuits, which tend to be a bit more abstract, and the very familiar harmonic oscillators, we can look at a spring which is suspended at a mass suspended through a spring from a ceiling. The equilibrium position of the spring will denote as phi 0 or x 0, x for position or flux for phi in our case. Phi are the deviations from equilibrium of that magnetic flux, or of course for a spring it's just the deviations of position. And the velocity is the rate of change of magnetic flux, or usually we'll also write that as v of t for a mechanical oscillator. Okay, so to illustrate what the equation on the left here is doing for the oscillation of the electromagnetic flux, we really have just a very standard familiar mass spring system that oscillates back and forth, except this time what's oscillating isn't the position of a mechanical spring, it's the amount of magnetic flux rather than the amount of deviation of the spring and the mass. And I think, Brian, maybe I should pause if there are any questions.
Sure thing. I'm going to pull up just a few here. Just for everyone to know, I did go through and kind of culled through the questions. If you were asking a question about something outside of today's lecture, I did either mark those as irrelevant and then deleted them. Sorry, not to say they're irrelevant. They are not irrelevant, but just mark them as not right for today. So we want to ask questions that are good for today. And with that in mind, this question says, am I understanding correctly that CQED allows the measurement of a qubit without destroying the superposition?
Yeah, thank you. As we'll see, it depends very much on the type of measurement you do. If you do a measurement of energy, then the measurement will place you if it's also a standard projective type of von Neumann measurement, which is exactly the kind of measurement that we actually do in practice, the effect of the measurement due to the necessary and unavoidable measurement back action is to disturb the state of the system so as to randomly land, if you start in a superposition, into either the ground state or the excited state, meaning the 0 logical or the 1 logical. So if you start in a superposition of 0 plus 1, a projective measurement of the z quadrature, which is basically the energy of sigma z, will project you into either the ground state or the excited state, the 0 or the 1. So it will destroy, in that sense, the superposition. Of course, if you start in 0 plus 1 and you measure in a basis of an operator which measures are you in 0 plus 1 or are you in 0 minus 1, then that will not destroy the superposition. So it depends on the measurement. But typically the measurement that we do does destroy it.
Okay, and then one last quick question. Some people were asking for just a quick reminder about the dot notation that you're using in your equations.
Yes, thank you. This is physics shorthand for time derivative. And you notice that everywhere here I've omitted to write, so you can think of phi is really equal to phi of t. This is my shorthand for writing these. But I don't know why it's a little pixelated on my screen here when I write, so I apologize for that. And of course phi dot in this notation is defined to just be the time derivative, or the rate of change in time of the variable that's underneath it, right? And if you have two dots, then that will indicate that you have, there you go, two dots. That will indicate that you have basically done this operation twice, and so you have a second time derivative like this. Okay, thank you. Okay, so then this takes us into a bit of a dangerous bend. You see I've indicated here that we are going to temporarily assume some knowledge of classical mechanics just on our way to a Hamiltonian, a quantum Hamiltonian, but I'll basically describe all the necessary steps and keep it at a kind of mixed level of idea and rigor. We saw that from very simple considerations of Kirchhoffs' law, we can derive an equation of motion that relates how the magnetic flux oscillates. You notice that we completely eliminated the charge and we only operate with one variable phi. So we can think of this variable phi as the position of the spring, right? And then phi dot as the velocity. Now this starts to sound a lot like mechanics in a way. And we can use the regular tools of classical mechanics to describe this type of dynamical system. At the level of equations, I could just swap all the symbols from phi's to x's for position. Now, the standard description begins with the so-called Lagrangian. The Lagrangian is just the difference between the kinetic and the potential energy. All right, so the Lagrangian, which is a functional of phi and phi dot, or basically the position and the velocity, is the capacitive energy, which is a function of just velocity. That's what it means to be kinetic. And the energy function of the potential energy, which is just a function of the position. That's what it means to be potential energy. All right, if I substitute in what capacitive energy is in terms of magnetic flux and what inductive energy is in terms of magnetic flux, which we derived I think 2 slides ago, I have 1/2 C voltage squared minus phi squared over 2L. And this is a very, very standard common equation you'll see. Now the next step in going from a circuit to a Hamiltonian is to identify the so-called momentum, or in the language of mechanics, or in the language of circuits, the charge. The charge here will play the role of momentum because I've chosen the magnetic flux as my position. In the language of Lagrangian mechanics, this is called a canonically conjugate variable. But I can obtain the charge Q by taking a partial derivative on the Lagrangian with respect to phi dot. And if I do that, you notice that d phi squared d phi dot is equal to 0, because we treat position and velocity as 2 independent variables, so that's 0. And then the partial derivative with respect to the position here squared, or sorry, the velocity squared with respect to d phi dot, that's just equal to the usual 2 phi dot. It's just like doing dx squared dx is equal to 2x. And of course, all this says, by the way, from the Lagrangian point of view, you notice this says Q equals CV, right? Or charge is equal to capacitance times voltage. Nothing new. We've already seen this, except this case, there's a little sleight of hand in that whose charge and whose voltage? Well, we've already built in the constraints about relating the fact that the flux of the inductor is equal to the flux of the capacitor and how their charges are linked. And so we've eliminated actually all of those other variables. Now this equation looks just like classical mechanics. So we have momentum, we have position, and we can write the F equals ma of circuits, or also called the Euler-Lagrange equations. The sort of mathematically rigorous way to do that is to write down this expression. We have a full time derivative on the rate of change of the Lagrangian with respect to phi dot, or the voltage, is equal to dl d phi. If you plug in these numbers, basically just use again the expressions I wrote up here and just substitute those into this equation, you will find again that you have recovered the equation of motion. And the way we actually constructed the Lagrangian officially is by starting at the equation of motion and making sure that the Euler-Lagrange equation expresses exactly this condition. Now, if you remember how we defined the current across the capacitor and the current across the inductor, you see that, again, this equation is nothing but Kirchhoffs' current law. So Kirchhoffs' current law here is F equals ma, or is the Euler-Lagrange equation, right? And then the two currents of the charge and the current of the inductor, which are up here, serve to describe the actual evolution of the system. Now, having done all of this nice mathematical trickery, we can use the momentum that we've defined, which is charge, and the position, which is phi, and the two energy functionals to define the Hamiltonian. And the Hamiltonian now is a functional of the position, which is the magnetic flux phi, and the momentum, which is the charge q. And we arrive at the all-important equation that the Hamiltonian of an electromagnetic LC circuit is phi squared over 2L plus q squared over 2C, where we have simply rewritten the energies in terms of the momentum and the position, or formally done a Legendre transform. Let me maybe pause, Brian, since this is a slightly more advanced slide. Are there any questions on this?
I will ask actually in the chat if there are any questions on this directly. Normally we see there's about a 10 to 15 second delay between me asking this out loud and people actually acknowledging it in the chat. So I'm just going to stall for about 15 seconds here. But yeah, we definitely want to see if there's any very topical questions about this. So I will pause for a second and watch the chat, and maybe after someone responds, I'll let you know.
Okay, good.
So to start with, I see here, based on a calibrated pulse sent to the qubit, you determine what the absorbed frequency is, and that will determine the energy level that's changed.
Oh yeah, I think the question is maybe about the calibration and the frequency and how we know what. Well, you'll see that the frequency of the qubit will essentially come from this equation. There'll be a nonlinearity we add, which will slightly renormalize it, but the frequency of the qubit will be set by exactly these two parameters, L and C. And I think on the previous slide here, I had this equation where we defined, the frequency omega naught of the resonance. Now, once we have the nonlinearity, the frequency of the qubit will be slightly renormalized due to the nonlinearity, and will change as a fact of that, but will be still very close to the linear frequency here of the resonance. And so the microwave pulses with shine will be at this dressed, renormalized frequency of oscillation.
Okay, and we had a few people asking if you could please just go over the Hamiltonian one more time and just explain in detail. A few people are confused about how that connects with the Langrian.
Yes, and I'll give a nice physical picture in the next few slides to explain it in more detail. Well, you notice that the two are very interestingly related. The Lagrangian is a particular type of useful function which Lagrange worked on, which defines the kinetic minus the potential energy. Now, that's not all. It's not just kinetic minus potential. It's kinetic minus potential in terms of the position, which is phi, and the velocity, which is phi dot. The Hamiltonian, on the other hand, is basically the kinetic plus the potential. So there's a sign difference, but that's not really the most essential difference. The even more important difference between the two is that we have swapped out the second part of the function here. It's no longer in terms of velocity, it's in terms of momentum. Right? So when you do mechanics, you see that there's a number of advantages and reasons that why you should use momentum as opposed to velocity. And in this case, we exactly have the same picture, that we need to work in terms of flux and charge. We can't use current and voltage. Basically, current and voltage don't serve the purpose in these equations of motion as the generalized position and momentum. We have to move one level up to flux and charge. Good.
Okay. Yeah, so for now, let's jump back into your lecture. Thank you very much for answering those.
Right. right? And again, I'll stress the analogy, that position that is summarized here between mass and spring constant and so forth. So let's explore what the Hamiltonian means and what it does. And two key parameters we saw are the product of the capacitance and inductance, which give the resonance frequency omega naught. And there is a little typo here. You can also take the other product, which is the ratio of the inductance and capacitance, and I'll call that the impedance for reasons that will become apparent later. But it's essentially a way to transform the variables mathematically, but physically their product or inverse gives you the resonance frequency, and then the impedance will have to do with the susceptibility or how easy it is maybe to couple to this element. So let's look at what the Hamiltonian says. I think this will answer the question. Well, the Hamiltonian consists of two parts. It has the potential energy function, which is phi squared over 2L, which is a quadratic in energy. So here I have the magnetic flux, which serves as position on the bottom. On the horizontal and on the vertical y-axis, we have energy. And a classical particle, of course, you can think of as a little red dot that is trapped on this parabola and can move up and down this parabola, right? And it sloshes its energy between, for a given energy, let's say E, it sloshes its energy between kinetic and potential, or inductive and capacitive in this case, and the velocity is given by the capacitive energy, 1/2 c phi dot squared. And I love this quote by Henri Poincaré. It is by logic that we prove, but by intuition that we discover. And so let's build a little bit further intuition on the Hamiltonian. Let's suppose, just for simplicity, we set the inductance and capacitance to equal 1 for now. Then I can say, well, let me pick an energy, right? Suppose I want to put an amount of this much in the resonator, which we'll call h bar omega naught, n plus 1/2. As a very suggestive form. You've noticed I introduced the quantum action of quantum in quantum of action, in quantum physics. Planck's constant h bar. Omega naught is the resonance frequency of the oscillator. N is just some number which I can choose, and 1/2. This is, of course, the energy of a quantum harmonic oscillator, even though we haven't quantized yet this oscillator, but I can choose to set the energy of the classical oscillator equal to that of a quantum one. Why not? That's totally allowed. And that equals 1/2 q squared plus phi squared in terms of the Hamiltonian, right? The Hamiltonian is supposed to describe the total energy of the circuit. Now, what does that remind you of? Well, if you fix the energy and you say that you have x squared plus p squared, or q squared plus phi squared, equal to fixed energy, in phase space, in the space of position and momentum, or phi and q, the equipotentials of energy give circles for the trajectories. So the very first circle here corresponds to n equals 0, or as we'll see in quantum, that will be the ground state. N equals 1, 2, and so forth. In other words, each of these rings corresponds to one more excitation of energy in the circuit. Now, there's no reason that in classical physics I have to constrain myself to be at one of these rings. I could be anywhere in between, but in quantum we'll see effectively you can't do that. Now, suppose that we want to describe how the particle behaves, the classical oscillator behaves. The oscillator, I can represent its state by this red dot. The red dot indicates the position and momentum of the particle. From the Hamiltonian equations of motion, which are just another way of rewriting Kirchhoffs' laws, we can figure out that the rate of change of the magnetic flux, if I'm at a point here, will depend on my position q, and vice versa. Q will depend on phi. And so if I start here, I can denote with a little vector which way I will go if I'm the particle oscillating. And so you can do this for a number of points on the ring, and you see that the trajectory that the particle will follow is in this case circular, and it will oscillate between position and momentum, or between flux and charge, right? This is just another way to represent that the electric charges on the capacitor are flowing through the inductor to the other plate and back and forth. And that's what we see. The charge goes positive, then it turns into flux, which corresponds to current flowing inductor, then goes to negative charge, so we flip the polarity of the capacitor and back and forth. Now we can introduce a very helpful variable by saying that we can recognize that this particle is just moving in a ring, in a circle. Of course, that should remind you of complex numbers, and if you have a complex number and you exponentiate it e to the I, such as this, e to the minus I omega naught t, that's a compact way to simply represent a point in a 2D plane. In other words, I can succinctly write down where the particle is in this plane by saying, well, you know, if the particle is over here, I can write that as a vector of phi and q, or it may be notationally advantageous to use a complex number. And I've picked here a very specific scaling factor and representation of how to define this classical complex variable alpha, which will exactly describe the point in phase space of the oscillator in such a way that it's the most analogous variable to the quantum operator, the ladder operators, the creation and annihilation operators that come up. But it essentially acts very much like them. And so if we rewrite the energy of the Hamiltonian using this new variable, which mostly at this point is just a mathematical trick, we can see that the Hamiltonian now becomes a function of alpha and its complex conjugate, 1/2 h bar omega, and I've just symmetrized here the product of these two complex numbers. And the reason I've symmetrized is because if and when we do quantization on this, we have to worry about the ordering of products. Right now, at the level of algebra, all I've done is a mathematical transformation. At the level of pictures, we have done a very nice. Let's see if we can play this animation again here. We've done a simple transformation where we've expressed circular motion using complex numbers. But this alpha will be quite key in the quantum case and will really allow us to, will be the basis of the description of most of the transmon qubit. And it's very important to know that its motion really proceeds in this simple harmonic motion as e to the I omega naught t. And that will lead us into things like the rotating wave approximation and simplifying the dynamics quite a bit. Okay, and that brings us into unveiling the quantum world. And maybe, Brian, I should pause here and take any questions.
Yep, I think answering one question here before you dive into that, and then after you dive in, we'll have a lot ready after the next break, so we can plan for that. But right here, a question we have now that we're pretty deep into the lecture. You mentioned physicists can all view physics as all spins or all oscillators, and I know that's kind of a joke and kind of not a joke, but would you be able to arrive to the same results of today's lecture by following the spin view of physics instead of the oscillator one?
Yeah, that's a good question. You can, in the case of treating the qubit directly from spins, if you start at the level of the atom, you cannot use really spins to describe the electromagnetic circuits, because they really aren't. They are really oscillators. You can mathematically, of course, at a very formal level, always map a spin to an oscillator or an oscillator to a spin. This is related to the so-called Holstein-Primakov transformation. We don't need to get into that. But there is a mapping essentially which allows you to say, well, if I have a spin with n going to infinity number of levels, I can make it look like an oscillator, and I can kind of, obviously we've seen how to take an oscillator and make it anharmonic and make it look like a spin, which was the first part of the lecture. So at a very formal level, you could do that. But I think in practice, especially for the language of circuit quantum electrodynamics, we can really think of everything as oscillators, nonlinear oscillators, and modified oscillators. And that allows a lot of simplicity because oscillators are simple and they form a simple basis. But as soon as you add a few extra ingredients on top, you can create very complicated and difficult and complex and rich dynamics and behavior, which makes fun.
Definitely. And then one more thing, just really quickly. People asking about what we just had on screen in the last slide, the equation that we had there. Does alpha describe the path?
Oh, wonderful. Yes, thank you. That's a great way to phrase it. Alpha describes the path or the trajectory of the motion in phase space. Exactly.
Great, thank you.
Yeah. So alpha itself describes the position or the state. It summarizes both the position phi. Oh, it summarizes both the position phi and the momentum q, or the flux and charge, and it tells you where the point where it fully specifies the state of the system. Basically, anything and everything you would want to know about the system can be calculated if you know phi and q, or equivalent if you just know alpha. Alpha is just the compact way of writing the two. But its time evolution is also really nice and simple. I can write that alpha of t is equal to alpha 0. Alpha 0 is just, well, maybe if I started my system not at phi equals, if I started my system over here, then alpha of 0 would be the point over here. And an alpha of t describes the path or the trajectory that the particle takes along this ring.